Chapter 7 and 8, we're looking at circular motion and related to circular motion, things moving in a circle that will bring us to torque. To look at circular motion, we're going to look at an object starting out moving in a circle. We're going to imagine object P moving in a circle. In this case, it's moving in a clockwise circle. And it travels a distance around the circle, and we're going to call that distance along the circumference delta x. And during the time it travels that distance x, it inscribes an angle theta. We have the radius r of our circle, and we're going to use those pieces of information. If we wanted to find out its linear or tangential speed, that would be its distance along the circumference divided by the time it takes it to get there. It would look like this. Velocity equals its change in position along the circumference divided by time. And the units for that, as we've seen before, are going to be meters per second. Talking about circular motion, we can also talk about angular velocity, where we're looking at the angle that this object sweeps out around the circle per unit time. We're going to measure theta, the angle, in radians, so that if we're looking for an angular velocity, that symbol is a Greek omega, which looks kind of like a script W, and that equals a change in the angle in radians divided by time. So the units for this are going to be radians per second. We can find the angular velocity, omega, if we know the time for one revolution, or if we know the change in angle and the amount of time it takes to make that angle change. If we wanted to make a relationship between angular velocity and linear or tangential velocity, we can also make the relationship between the change in angle and the change in position along the circumference. We have change in angle over time equals 2, and we have 2 pi r meters equals 2 pi radians. So if we put that together, we have 2 pi r times x over r. That gives us theta radians. So what that gives us then is the change in x along the circle is theta radians times the radius. So there's one of our relationships that relates linear with tangential or angular motion. We can compute linear speed if we know the circumference of the circle, and if we know the time it takes to go around the circle one time. And if we compare angular and linear speeds, we will get the equation shown. And the way that we're going to get that is we have velocity equals 2 pi r over t, omega equals 2 pi over t. So if we substitute omega for 2 pi over t, we get velocity, linear or tangential velocity, equaling angular velocity times the radius. So that allows us now to relate velocities, linear with angular. We can also compare angular acceleration with linear acceleration. Angular acceleration, definition of acceleration we've seen is change in velocity over time. Final velocity minus initial velocity over time is the same thing. Angular acceleration, the symbol for that is alpha, and that is change in angular velocity over time. Final angular velocity minus initial angular velocity over time. We saw before that the change in velocity equals the radius times the change in angular velocity, so we can say acceleration equals radius times the change in angular velocity over time. And that leads us to the relationship of acceleration equals radius times angular acceleration. So there is the third of our relationships between linear or tangential and angular motion. We can come up with kinematic equations for angular motion the same way that we did kinematics for linear or tangential motion. It's the same pattern. The equations are going to look very familiar. So our first one is change in radians equals 1/2 of the angular velocity plus sum of initial plus final times the change in time. That corresponds to our change in position equals 1/2 final velocity plus initial velocity times time. If we take our definition of angular acceleration and rewrite it, we get final angular velocity equals angular acceleration times time plus initial angular velocity. That looks an awful lot like final velocity equals acceleration times time plus initial velocity. If we combine these two, then we'll get the kinematic equation for angular motion that looks like this. We have change in our theta equals 1/2 angular acceleration times change in time squared plus initial angular velocity times time. That corresponds to delta x equals 1/2 acceleration times squared plus initial velocity times time. Finally, if we take these equations, reorganize them, and combine them again as we did for linear velocity, we'll get angular velocity squared, final angular velocity, equals initial angular velocity squared plus 2 times angular acceleration times the change in angle, which corresponds to our VF squared equals VI squared plus 2 delta x times acceleration.